Welcome and thank you for joining us today for this SPE Tech Talk with Fluor Canada. I'm your host for this broadcast, Joe Sinnott, coming to you live from Pittsburgh, Pennsylvania, and I'm excited to dive into the topic of retrofitting carbon capture onto large industrial emission sources. This process looks to be a promising path forward for industries that are trying to reduce their greenhouse gas emissions from existing commercial infrastructure. But it begs the question, what exactly does it take to retrofit an industrial facility to capture 90 to 95% of carbon dioxide from a large emission source? We're joined today by Fluor to answer that question and to discuss the challenges and opportunities associated with carbon dioxide capture in these particular applications. And as we talk about carbon capture over the next 30 minutes, please remember that here on SPE Tech Talks, we're also big fans of comment capture. We want to capture your thoughts about today's topic. We want to capture your experiences with today's topic. We want to capture your questions about today's topic. And the best way for that to happen is for you to inject your thoughts, experiences, and questions into that comment box so that today's expert will have a chance to address them later on in this live show. And if you don't have anything to share with us just yet, then at least let us know where you're watching from and take a moment to participate in today's audience poll question, which looks a bit different from the type of poll question you may have been used to here on SPE Tech Talks. Because today we're asking you to play a matching game. So in the comment box, match the correct carbon dioxide input or output amounts with each type of facility. Your facility choices are a greenhouse, an algae farm, a commercial facility, and a brewery. So please go ahead and match which number is associated with each facility, and we'll see how well you did later on in the show. But for now, let's go ahead and match you, the audience, with today's guest, John Isley, who is joining us from Calgary, Canada. John is a professional engineer and senior director for carbon capture and renewable fuels with Fluor Canada. He has over 27 years of process technology experience in the refining and gas processing industries. And he has served as a Fluor technical lead on the Shell Quest carbon capture project located near Edmonton, Canada. He has become a recognized subject matter expert in carbon capture, and he supports several energy transition technologies for Fluor. And prior to all of these accomplishments, John earned a chemical engineering degree from the University of Notre Dame, which I suppose means he has made the transition from the land of the Fighting Irish to a role that has him and his team fighting carbon emissions. But with all that being said, John, welcome today to SPE Tech Talk.
Thank you, Joe. That's a generous introduction. I'm happy to be here.
All right. Well, we are happy to have you. Although I guess to kick things off, John, can you tell us why we're here? Why are we talking about these processes? Why are we talking about companies even making the effort to try and capture carbon in this way and retrofit these large industrial facilities? Can you shed some light on why I'm here, why you're here, and why the audience tuned in today to listen to you?
Sure. Well, we talk about carbon capture because it's going to be a key item in the energy transition. And I think we need to think about the energy transition as a transition. It's a very long journey that because we have the existing infrastructure, the fossil fuels, the oil and gas, to this day, fossil fuels is still the largest energy source. And it will take quite a long time to wind that down. We have existing infrastructure, and then we have energy security needs, which has been quite proven with the recent war in Ukraine. And there's a lot of stakeholder pressure at the same time to push this transition forward. And there are also industries such as not just in the oil and gas, but in cement, mining, steel, that they don't have a lot of options. The carbon dioxide emission is part of the industrial process, but to fight climate change and to address the needs that are being pushed by stakeholders, governments around the world, it is starting to change industry behavior. So as the value of carbon starts to get realized through different taxes. There's taxes in Canada. There's taxes, carbon taxes in the EU. And then incentives. The US Inflation Reduction Act changed a structure called the 45Q from $50 per ton of CO2 tax credits to $85 a ton. And what that does, it gives mechanisms to monetize the value of carbon dioxide. And it creates mechanisms for not just for financing, for capitalization, and those credits can be traded. Those are financial instruments which can be used to treat carbon dioxide like an industrial product. And then industries are properly incentivized to move forward. And it's just a matter of knowing what the costs are, what the technologies are, where does it fit within their portfolio. And then it becomes an attractive option for industry to begin to look to pursue.
Got it. So you just laid out lots of different reasons why a company would consider capturing carbon from large industrial facilities. There's no shortage of large industrial facilities out there, but I'm going to assume that not every large industrial facility is a good candidate for this. So what are some of the basic conditions that need to be met for, what we're talking about today to even be a decent option or an attractive option to go ahead and, again, consider retrofitting these large facilities to capture some of the benefits that you just laid out?
Yeah, very important. Probably the number one question, of course, is an outlet for the CO2. And kind of the poll question hints at how big of a challenge this is, where the large industrial emitters emit such significant quantities of CO2 that if we look around the various outlets, whether it be a greenhouse, whether it be a brewery, in the past, the carbon capture industry developed from food grade CO2. Well, food grade CO2 is great. It's applied for breweries, soda pop, obviously. Many industrial processes use CO2, but the quantities that are needed and that for food grade CO2 processing pales in comparison to the amount that's actually emitted. So the geological sequestration tends to be and will be the number one area where we line up where the emission source is and can it get to a geological sequestration site. So there are many companies that are looking at carbon dioxide hubs in regions where it's attractive for that sequestration, whether that's in the Gulf Coast, even up through the Midwest, toward the Great Lakes region, sedimentary basins that are attractive for long-term CO2 sequestration and storage. Those are the ones that are being explored, and those make a great fit. Then also, it's the concentration of the CO2. It's the type of source, whether that's an industrial source from processes such as fermentation or a post-combustion flue gas. Those sources have their own challenges with oxygen and other contaminants in the flue gas, which must be handled. And then looking at the footprint itself of the carbon capture facility. Is there enough space? And what is the integration profile with the existing facility look like from electrical, utilities, steam, power, water? All of these aspects need to be taken into consideration to see if a facility is a good fit. Luckily, in the United States in particular, many of the industrial sources are within reasonable proximity of some of these conditions, especially in the oil and gas industry. There are existing CO2 networks, pipeline networks, Louisiana, Texas, that line up quite well with many of the large emission sources. On the mining side, they're in the Rocky Mountains and even out west to California are regions that look attractive for CO2 sequestration. So when we look across the profile, it doesn't necessarily apply to all major emitters, but there is a fairly good fit with a large percentage in the United States.
Great. Well, thank you for all that color. One thing you said was that one of the conditions is an outlet, a good outlet, which I think is a good time to remind our audience watching that you have a perfect inlet for all of your questions and comments and thoughts about today's topic. It's that comment box. So for those of you who are watching, again, inject your comments, inject your questions into that comment box, and John will get to as many of them as possible later on in the show. But for now, John, back to you. And I guess building upon, again, you just laid out the reasons why you would want to do this and some of the basic conditions. Can you talk about some of the actual technologies involved? So, what are the type of carbon capture technologies that are out there? Give us a little color on maybe, how they work and some of the differences between the different options that are out there.
Yeah, certainly. We try and marry the technologies with the sources, first of all. And then there is a suite of different technology readiness levels for carbon capture technologies. On this slide is a number of the technologies that Fluor gets involved in. First off, to highlight on the left-hand side, the many different applications, whether it be a chemical plant, LNG, refineries, fossil fuel plants. In some of the CO2, as I mentioned, is a byproduct from the industrial processes. But for the flue gas, which is throughout the power industries, really throughout every industry, has some source of combustion. Those technologies tend to be more the amine-based solvents. And there are a number of different proprietary type solvents, open source solvents, which have been used on a commercial scale. I mentioned the food grade industry. That type of industry capture has been around for well over 40 years and commercialized in the 1980s and 90s. And there are literally dozens of those types of facilities on flue gas, on common emission sources. It is more of a scale-up issue. It's more of an issue of if we look at the large industrial emitters, over 1 million tons per year in those sources, at that size and at that scale up, there's only a small handful of commercial facilities, mostly because those incentives that I mentioned previously are just now kicking in. So the amine-based is the most commercially available. But I won't dismiss some of the up-and-coming technologies. There's physical solvents, there's membranes, there's some cryogenic technologies at various TRL levels, and they are pushing toward commercialization. I'd say they're not quite there. We are looking at commercialization at Fluor in today's current environment, and we feel like, for example, the $85 per ton price of CO2 looks very, very attractive for the conventional solvent-based technologies that we are doing the engineering and the front-end design work on for many industrial facilities throughout. So that's kind of the suite. But if we say what's commercial today, it's amine-based technologies, and we certainly have good recommendations going that route.
Got it. So thanks for laying out the technology side of things, the different options that are there. Again, earlier in the show, you talked about the impetus for doing this and some of the base conditions. But once all those are in place, so you got your technologies, you've got the base conditions met. What are some of the considerations to actually move forward and actually make this again a viable project and something that is going to be more likely than not successful? So can you shed some light on those extra considerations once you've checked sort of these basic boxes that you laid out so far?
Yeah, absolutely. Once the basic boxes are there, I'd say if we look at the capital costs and the operating cost of CO2 capture, the most important is to look for synergies, things that work in certain facilities. We're approached by many clients that have multiple facilities. And as we look across those and look across those sources, we look at groupings, we look at location, we also look at concentration of the CO2, and we look at what other contaminants might be in those streams to match the type of technologies, capture technologies, with the particular application. And also what's really important in that profile is the utilities. The CO2 capture, it requires power, water, steam to run those facilities. And the source of that power, water, and steam, the location of it. Does the facility have some capacity in those areas? Or are there synergies with respect to generating power, water, and steam as a product, say, as say a combined heat and power plant located next to the CO2 capture, which can provide the utilities plus provide the energy needed for the CO2 capture process itself. So next we look at the technologies themselves. I mentioned the amine-based technologies. There is a number of proprietary amine solvent-based technologies which are have the commercial experience necessary to really guarantee performance, to deliver and at the OpEx and with the reliability needed to monetize these projects long term. And then as we line up some of those commercially available technologies, and Fluor offers the Economy and FG Plus technology, which is in that suite. We have 30 years of experience in Economy and FG Plus. But when we line those up, we find that many of those processes have been optimized to a point where, quite honestly, they're fairly neck and neck. So then it comes down to execution efficiency, the ability to define the project well, to constrain it, to come up with a capital and an operating cost profile that's attractive for both the internal and external investors, and the ability to organize that project in a way that provides some cost certainty, some schedule certainty, and that project can deliver. And a lot of that comes from experience. It comes from engaging companies, people that have knowledge and experience in this space, that have the ability to execute those projects, have the connections through all the way from the engineering scope, the technology supply, the integration, all the tie-ins needed with the facility, whether that be electrical, whether that be the steam and the water systems, treating the waste, have the ability to go into that facility, look at those technical details, really dive down to uncover those things that might be potential surprises, and then define it well, do the engineering, and integrate that with the technology so that the project can be well defined before an FID is given, one that's honest and can be used to really line up the investment in moving that carbon capture facility forward. Because at the end of the day, often the carbon capture plant is looked at not as a moneymaker. It's looked at as part of more of an obligation, more as an environmental project. And one of the examples that I worked on, which was the Quest carbon capture project in Edmonton, Canada, it was about doing carbon capture on a hydrogen plant where the hydrogen production was the primary business. And the carbon capture as greenhouse gas mitigation was great, but it couldn't interrupt the core business. So the ability to turn it off and on, for example, is one of those engineering features that we incorporate into the designs. And it's really marrying all that to define a project that's palatable, that works, and that companies can get behind and invest in.
Got it. So what I think I heard in that answer, John, is that even though I just got a 15-minute primer listening to you at the outset of this SPE Tech Talk, I probably don't have the experience just yet to go ahead and try to lead a project like this. I think that's what I'm hearing, right?
Yeah, it's the experience-based work is really important. It's kind of one of those like some engineering companies look at this like an amine plant, and there are the flow sheet. I mean, I'm a chemical engineer, so the process flow sheet looks just like an amine plant. But the unique challenges, sort of if you only knew type challenges involved in it, often have to do with the fact that flue gas sources in particular contain contaminants which tend to poison these processes. And the historical record has shown that there are unique challenges to post-combustion carbon capture. There's oxygen in that stream, and if you're a chemical engineer like me, we like processes that don't have oxygen, because oxygen corrodes, oxygen causes side reactions. Obviously, it is an oxidizing agent. So from a chemical processing standpoint, we like what we call clean processes that are void of contaminants, that don't poison catalysts, don't poison solvents. And flue gas tends to poison. It tends to poison the amines. There's primarily the NOx. Any sulfur in the fuel will react, form SOx, and then both the NOx and SOx react with the solvents over time. They accumulate in the amine loop, and that accumulation causes other problems. They form heat-stable salts. Those salts can cause corrosion, cause degradation. Ultimately, they reduce performance. So in the Fluor technology, we focused on the cleanliness and the hygiene of the solvent. We focused on how do we make these facilities more reliable. We find that it's dealing with those contaminants primarily. It's dealing with those things that you don't know. So we've employed, for example, an online solvent maintenance system into the Economine FG Plus technology that maintains online through a slipstream, cleaning the solvent continuously and removing those side products and those contaminants. And I might add that it's not just Fluor technology. If we look at many of the emerging technologies, it's some of the key challenges in the industry is how to handle these contaminants, whether you're trying to put them through a membrane, whether you're trying to use cryogenics. They have to be dealt with. And they have to be dealt with such that a facility operates continuously, that it operates reliably, and that it's cost effective, that the contaminants and the challenges are such that they don't require or push the designers to put in overly expensive cleaning systems, looking at elegant solutions for capturing carbon dioxide from challenging sources. And beyond that, there's industries such as steel, cement, that have kilns, that have particulates, that have, in the steel industry, other metals can get into those systems. So the technical challenges, the engineering challenges associated with carbon capture are quite fascinating and will really push the industry as it's moving toward wider adoption into innovative thoughts, innovative designs, and really there'll be a bit of development, operation, and trial and error, if you will, and fine tuning some of that. And that's why experience is so important. You could start today in studying these types of items. I guess in my view, where we have been is it's 10 to 20 years behind some of the work that others have done.
Got it. Well, I appreciate you shedding some light on, I think, as you put it, your experience as a chemical engineer. I must say my experience as a chemical engineer, I think, surrounds more of the chemistry behind beer, which is a perfect segue back to our poll question or our matching game from earlier. So I want to revisit, I want to find out the answers as to how much CO2 is involved in a brewery. So if we could bring up the graphic for the correct answers that our audience has engaged in and had a chance to think about over the last several minutes here. And again, as you can see here, the algae farm, the brewery, the greenhouse, the commercial facility, the answers are on the screen in terms of how much CO2 is either input or output from each of those types of facilities. So hopefully our audience enjoyed this change of pace here on the poll question. And I want to shift back to our audience, of course, because as we head towards the end of this show, we do have some questions piling up from our audience, John. So maybe we start ticking through a couple of those, unless you have any final comments about the graphic we just showed there. Anything that any misconceptions that people have about maybe the CO2 that goes into or comes out of those type of facilities?
It really highlights the magnitude of the challenge. And that's one reason, sure, we should use greenhouses. We should be capturing CO2 and use it in algae farms. Like, we should be pushing all of those things. But the it's the order of magnitude of the challenge. If we look at how much footprint of greenhouses would we need to match even one industrial facility, it's quite a challenge.
Sure. Great. All right. Well, thanks for that perspective. And now on LinkedIn here, we have a couple questions that came through. So maybe sort of a rapid fire, John. The first one is, what is the best way to capture CO2? And then how can we cover the cost of the CO2 capture? You talked about this a little bit, but again, for people that just want to cut to the chase and say, all right, what's the best way to do this? And what's the best way to make it, if not profitable, as you said, sometimes profit isn't the be all end all, but at least the most cost effective approach. What's your answer to people that kind of bring up that quick and simple question there?
Well, in Canada, and I can tell you, we're starting with the industrial sources. Those are the best sources. So fermentation for ethanol production, hydrogen production from steam methane reforming. So those sources, they're readily available. The threshold, I mentioned 85 US a ton. That threshold is achievable to make those types of capture economic. Those are typically amine-based solvents, but not always. But they are often a solvent of some type. Those are the best sources to kickstart today.
Got it. All right. Speaking of amine type solutions and solvents, we have another question there. So, how can we improve the efficiency of the CO2 capture with amine solutions? Can you shed some light on to the extent you can, maybe some of the specific technology that's kicking that up a notch and making it more effective to accomplish that?
That's something, Joe, I spend a lot of time on is aiming at efficiency. I mean, the first thing to do is just process efficiency and optimizing the flow sheet itself. We've done that through heat exchangers, through integration with utilities, as an example. The challenge of the amine based, and I would say this for really any solvent, is we look at what are the theoretical minimums of those technologies. And it often has to do with the heat of solution, of getting the CO2 into a solution of any type. And that takes a certain amount of energy, enthalpy. And that enthalpy is sort of the cost, if you will, of basically taking a source, which is often full of nitrogen, some oxygen, and a bit of CO2, and separating them. We're getting close to some of the theoretical minimums of amine solutions. And theoretical minimums is, we've worked with our PhDs and scientists, and they continue to study this with research facilities throughout the world. Lots of funding from the Department of Energy and the national laboratories in the US, but we're starting to get toward some of those minimums. And that's where then we start challenging the paradigm. What is it about the amines? What other solvents, or what is driving those heats of solutions? Get down into the real physics of it and challenging those, and seeing if there's other ways that we can change those paradigms.
Got it. All right. Well, we are getting close to the end here, but there is at least one other audience question I want to get to. And I think it's relevant because we're getting very close to St. Patrick's Day. You, of course, are an alumnus of the University of Notre Dame, who I think actually has a contractual commitment to Guinness, the drink. So bring up this question from our audience, which is, what is the best product to produce from CO2 utilization? Is it Guinness? Is it beer, John? Or is it something else in your opinion that is the best way to utilize CO2?
Well, Guinness is definitely at the top of my list. So, I would put that up at number one. But, from a commercial industrial standpoint, it's tough to say. The CO2 is being used in enhanced oil recovery. There are economic uses of it for the large industrial amounts, such as that. So I'd have to say, like, in the short term, it's probably certainly it's food grade, no doubt. Soda pop, Guinness, but enhanced oil recovery is still there for the time being. It helps to get the technology costs down by finding those uses, and then as the costs get down, as it gets more widely adopted, then that will help spur on more investment and more technology development. So it is definitely the way we need to go.
Got it. All right. Well, thank you for that. Thank you for all your answers to the various questions that came in today. Thank you to the audience for asking questions. I know we didn't get to all of them, but whether you're watching live right now or you're watching this on replay, keep putting your questions in there. We'll get those captured and try to get those answered. Although, John, if people have pressing questions for you, if they want to reach out, maybe something more serious than the way I wrap things up today, what is the best way for them to get a hold of you?
You can reach out to me on LinkedIn, or you can email me direct. I'm happy to answer questions and support the industry in exploring this topic. So appreciate it.
Great. Well, thank you again for enlightening us on the topic of retrofitting large industrial emitters with carbon capture facilities. And special thank you, of course, to Fluor for sponsoring today's conversation. If you would like to watch a replay of today's conversation, you can do so on the SPE Energy Stream, the industry's digital pulse. Visit streaming.spe.org. I'm your host, Joe Sinnott. Join us again next time right here on SPE Tech Talk.
Thank you, Joe.
The energy industry is evolving rapidly. To stay informed, you need relevant content available when and where it's convenient for you. Introducing the SPE Energy Stream, the energy sector's platform for quality content from around the world. Energy Stream gives you access to technical solutions, innovations, trending topics, thought leadership, market outlooks, and education. From original programs to exclusive SPE event presentations, this easy-to-navigate platform features insightful content delivered live and on demand. Explore insights from industry thought leaders, then save the videos that interest you so you can watch them at your convenience. Stay ahead of the curve. Start watching SPE Energy Stream today.